All right, we are back for part 2 of our metallurgy video. Right now we're going to talk about properties of materials. So we use a lot of these terms interchangeably, and we need to know what they mean because they mean very different things. What we're going to talk about is hardness, strength, ductility, toughness, elasticity. They all mean very specific things. We need to know what they are. So, you know, my example for this is concrete. Okay, if I've got a concrete block, concrete's very strong in compression. If I can put a ton of weight on top of this concrete block, and it's incredibly strong. Okay, so concrete, we can say concrete is strong. Well, it's strong in compression. What if I take that same concrete block and cast some lifting pieces in it? Terrible drawing. And I try to lift something up with it. It's not strong. It'll just fall apart. It will rip apart. These will rip out of it because this is tension. It is not strong in tension. So concrete is very strong in compression. It's not strong in tension. So we can't say concrete's strong. We have to explain how it is strong. That's why we need to know what we're talking about. Because we can say something is strong. Well, what does that mean? I don't know. How are we gonna put load on it? So start off with hardness. So hardness is defined as the ability to resist penetration, and they measure hardness with a couple of different ways. All of them involve pressing something into a piece of material and measuring how big the dent is. Really hard stuff in the steel world, that stuff like knife blades and files, you won't get a very big divot because they're very hard. They resist penetration. Hard stuff also is brittle. It's the trade-off. Glass is very hard. It's also very brittle. As hardness goes up, brittleness goes up. Next one we're going to talk about is brittleness. We just talked about that. Brittleness is the ease at which a metal will crack or break apart without noticeable deformation. It's related to hardness. Ductility. So ductility is the ability of a metal to be permanently twisted, drawn out, bent, or changed in shape without cracking or breaking. So it is the ability to bend and not break. Most steels, especially the mild steels they build buildings out of, is real ductile because they don't want buildings to focus. They don't want buildings to, in an earthquake, break like glass. They want them to bend like noodles and flop around and not collapse on people. So we're looking for ductility. As welders, we're always looking for ductility in the stuff we weld because we don't want catastrophic failures. Toughness. Toughness is the property that allows metal to withstand forces, sudden shock, or bends without fracturing. Toughness is usually, as welders, impact toughness, and they use the Sharpie V-notch test for that, where they take a piece of metal, they cool it, they hit it with a hammer, and they see how much force it takes to break it, from how we measure toughness. Strength. Strength is the property of metal to resist deformation. There is tensile strength, which, again, let's draw a beam this time. There's tensile strength, which is pulling it this way. There's compressive strength, which is compressing it that way. There's torsional strength, which would be twisting it. So twisting it like that, that'd be torsional. And then there would be shear strength, which is trying to shear it. And that would be, let's say I weld it here and I put a lot of stress here. I'm trying to shear it up that point. That's shear strength. A lot of materials are good at a couple of these things. Most stuff isn't good at all of them. If something is really strong in tensile, so really good at pulling, it might not be so good in compression, or it might not be so good in shear, it might not be so good in torsional strength. So we have to think about that and find what is going to work for us for the application. Strain is deformation caused by stress. Okay? Elasticity, and this is a really important thing for us, elasticity is the ability of a material to return to its original form after removal of the load. So if I put 100 pounds on this or whatever, and it flexes down, if the material is elastic, when I take that 100 pounds off, it will spring right back up to shape. What that means is I have not reached its elastic limit. If I put 1,000 pounds on it, and then I take that off, let's say it will no longer spring back to its original shape. An elastic limit is something for welders. When we're designing a structure or building a structure, we never want to plan on working something past its elastic limit. We want them to bend and flex and continue in service. If we hit that point where we're past elasticity and ductility, where we've permanently deformed something, we need to repair it. And we need to design it better next time so we don't hit that limit. Springs in a truck. We don't design those at their ductile limit. We don't want to hit a bump so big that the springs, take a set, they're permanently deformed. We want to always be within that elastic limit. Hard materials can't be ductile. Tough materials can't be brittle. All those different properties, they got to find that balance. Let's see. Let's talk about heat affected zones in welding. So we talked about grain structure in the previous video. Well, welding changes grain structures. And in all things we build, what we're looking for is refined grain structure. We want nice small grains. There's a couple of really good animations of this in the PowerPoint. We've got our groove weld. This is all fine grain material. We put our weld in. The weld is fine grained as well. It's a different fine grain, but it is fine grain. But the part of the base metal that gets heated by the weld but doesn't actually get remelted, the grain changes. In here we go from a very fine grain, we've heated it up and then cooled it off, and the grains have grown. We get these big gross, they're not usually this big, we get these big gross grains in here. Okay? And just like when we talked about welding on forgings, when we have, when this is under load, the failure isn't going to be in the weld. It's not going to be in the base metal. Well, it will be in the base metal, but it won't be out here in the base metal that still has the refined grain structure. It's going to be right here at that transition between heat affected zone and weld or heat affected zone and base metal. That's where it's going to fail. So how do we control that? Well, we control this grain size through heat management, and invariably it is slowing the cooling rate. That's why arc strikes are so bad. An arc strike has this giant grain structure and it'll crack. What we want is to slow the cooling rate so these grains have a chance to cool slowly and shrink and turn back into nice fine grained material. That is the whole key. Slide 85 has a really good kind of view of this. But through preheat and post-heat, we can manage this, and we can make sure that our heat-affected zone, the transition is not sharp and defined. It's a much wider heat-affected zone and a much finer grain inside that heat-affected zone. The other way we can do this is post-weld heat treatment, and what that does is kind of hits the reset button on grain size. We take the whole thing up to an elevated temperature, and what that allows us to do is we heat the whole thing up, we cool it real slowly, and it does the same thing as preheating the first time we do, is it allows those grains to refine and get nice and small again, so we have a much more ductile weld, less likely to fracture. Gosh, we're almost done. The last thing we're going to talk about in this lesson is corrosion in stainless steel. So what makes stainless steel stainless? It's chromium. Chromium is the addition to steel that makes it stainless. But we can screw that up. When we weld it, if we keep stainless steel focus, there we go. If we keep stainless steel at an elevated temperature for too long, that chromium will actually leach out of the material. So let's say I'm looking at the inside of I'm looking at a cross section of a pipe. Okay. So this is a cross section of a pipe. Terrible illustration of a cross section of a pipe. So stainless steel pipe. I put my welds in. I've got to control heat. I can't let this thing get too hot, because if I let this get too hot, what will happen is the carbide that is in the stainless, it doesn't like high temperatures. So what will happen is it will actually diffuse out of the stainless and leach out to the outside and make these big black crystals that is referred to in the industry as sugaring. They'll make these black crystals on the inside of that pipe. So that's two problems. One of them is now I've got schmutz on the inside of my pipe. The real problem is this area right here that the chromium was pulled out of, it's no longer stainless. It has less corrosion resistance than all of the surrounding material. So that in service, this is what's going to fail. And they look like weld failures. They're really not. Well, they're failures of the welder not controlling heat. What they are material failures due to improper treatment. We can't keep stainless above 800 degrees for very long at all. So we weld on it, we walk away from it, we do things. Stainless doesn't have enough carbon in it generally to harden, so we don't have to worry about preheat or post-heat. What we have to worry about is not keeping it in that elevated temperature range for too long. Like I said, that's above 800 degrees. Sugaring, all the stainless steel places in town, they want to know you can weld without sugaring stuff. That means you're going to have to control heat input. More importantly, you're going to have to control travel speed. Go as fast as you can. The biggest input in heat in a weld is travel speed. You'll actually get less heat input if you turn your machine up and go faster than you will turning your machine down and going slower. Something to think about. So anyway, there's been a lot of information. The PowerPoint is real good. The PowerPoint is good. The book is real good. Go through the book, read this. You're going to have questions. Bring them to me. I'll answer them best I can. All right. Thanks.